Hari Om. So in the information security course, in the second module, we are talking about the data encryption standard. In our previous videos, we discussed the history and the overview. We are currently talking about the DES structure. In the previous sessions, we discussed the initial and final permutations and the different rounds in the DES structure. So in this video, we are going to talk about the DES function, which is the very important component that comes in the DES round. Each round of DES is a Feastel cipher. So each round uses a function known as DES function. So we are going to talk about the DES function. So the DES function is the heart of DES. And you can see here, this is the one which we are going to discuss in this video. So inside the DES round, we have a mixer and a swapper. Inside the mixer component, we have a DES function f of Ri-1 comma ki. So this function applies a 48-bit keys to the rightmost 32 bits, which is Ri-1, and this 48 bits key is represented as ki, and this produces a 32-bit output. We are going to discuss what are the different elements or the components that are available in this function. If you observe here, the DES function is made of 4 different sections here. So this f of Ri-1 comma ki is having 4 different sections like this. These are the 4 different sections. It has an expansion P box. It has an exclusive OR component, which we call as the whitener. And we have group of 8 S boxes here. Then the last component is a straight P box or D box. So this P box, the expansion and the straight component can be a P box or a D box. P box is nothing but permutation box. A D box is nothing but diffusion box. So for the diffusion process, we use different permutation table. So it can be called as a P box or a D box. So these are the 4 different components that we are going to discuss for DES function. Now before we start with all these components, we should understand why this many number of components are included in the DES function to make it more secure. Now in cryptography, the confusion and diffusion are the 2 very important properties of the operation of a secure cipher, which is identified by Claude Shannon in his 1945 classified report, A Mathematical Theory of Cryptography. So these properties, if these properties are included in any of the cryptography, it will prevent the different methods of cryptanalysis. So that is the main objective of adding confusion and diffusion in any cryptographic system. Let us see what is confusion and what is diffusion. Confusion refers to making the relationship between the key and the ciphertext as complex as involved as possible. So if you want to make the ciphertext as complex as possible, then we can have confusion. Whereas diffusion refers to the property that redundancy in the statistics of the plain text is dissipated in the statistics of the ciphertext. So here we are going to shuffle the data. This is what we call as bit shuffling. So we shuffle the data as much as possible so that the statistics of the plain text will not be maintained in the statistics of the ciphertext. Because we have seen the statistics attack may happen in the crypto system. So to overcome this difficulty, we are going to diffuse the plain text. Diffusing is nothing but shuffling the bits as possible, as many number of times. This is what we call as diffusion. So the confusion and diffusion are becoming the building blocks of creating a cipher like DES cipher. So the confusion here is introduced in the S box. So S boxes are used for implementing the confusion property, and the P boxes, expansion P box and the straight P box, are used for implementing the diffusion property in the DES structure. So this confusion and diffusion is given here just for your understanding why we have this many number of components in the DES function. Let us discuss each and every function in detail. So inside the DES function we have different components. Each components are explained in detail here. Let us take the first one. The first one is expansion P box, and the expansion P box will take a 32 bits input and it is going to produce a 48 bits output. So here the input for the expansion P box is a 32-bit input, which is Ri-1, which we get from the previous round, and Ki is a 48-bit key, right? If you observe, to the exclusive OR operation, a 48 bits are given and a K value, the key value, which is again 48 bits, are given as the input. So exclusive OR takes 248 bits. Since the key value is 48 bits, the Ri-1 value, which is given as the input for exclusive OR, should also be 48 bits. So what we are going to do, since Ri-1 is a 32-bit input and Ki is a 48-bit key, we need to expand the Ri-1 to 48 bits. So this is what is being done by the expansion P box. So expansion P box is used to expand the Ri-1 value, which is a 32-bit input, and this Ri-1 32-bit input will be expanded to 48 bits by the expansion P box. Now what it is going to do, the 32 bits is now divided into 4 bits section, and each 4 bit section will be expanded to 6 bits. I repeat, here the 32 bits input is divided into 4 bits section, and each 4 bit section is expanded to 6 bits. Let us see how it is being done. So this is how the 32 bits input is expanded to 48 bits output. You can see here the 32-bit input is now divided into 4 bits chunks, or you call it as 4 bits blocks, or you can call it as 4 bit sections. And these 4 bit sections, each 4 bit section is expanded to 6 bits here. Each 4 bits is expanded to 6 bits so as to get a 48 bit output. Now when it is doing the expansion, it is using a predetermined rule. What is the predetermined rule? The bits 1, 2, 3, 4 is copied to 2, 3, 4, 5. So bits, this is 1, 2, 3, 4 of the first block, and this is 1, 2, 3, 4 of the second block, 1, 2, 3, 4 of the third block, 1, 2, 3, 4 of the fourth block, and so on. So this bits 1, 2, 3, 4 is copied here in the 6 bits chunk as bit 2, 3, 4, 5. So all these 4 bits are copied directly here to bit 2, 3, 4, 5. Then bit 1 of 6 bits chunk, bit 1 comes from the 4th bit of the previous block, and bit 6 comes from the first bit of the next block. Observe here again, the bit 1 of the 6 bit chunk comes from the 4th bit of the previous block, and bit 6 comes from the first bit of the next block. Right? Again here you can see bit 1 of this chunk comes from the 4th bit of the previous block, and bit 6 here comes from the first bit of the next block. And when you observe here, for the first and 8th, for the first and 8th blocks, these are considered to be adjacent sections. So the first bit of the first chunk, comes from the 4th bit of the last chunk. The same way, the 6th bit of the last chunk, comes from the first bit of the first chunk. So this is a predetermined rule used for expanding a 32-bit input into 48 bits output. Okay. So the DES uses this following table to define this P box and D box, and this is the expansion P box D box combination. You can see here 1, 2, 3, 4 is maintained as it is, and the last bit 32 bit is used here as the first bit. Bit 32 is used here as the first bit. So first bit is the 32 bit, then first bit, second bit, third bit, fourth bit, and here it is 5th bit, right? So 5th bit is the first bit of the next block. So 5th bit comes here. Then here 4th bit. Why? Because here the 4th bit of the previous block. So 4th bit of the previous block. Then 5, 6, 7, 8, which will be 5, 6, 7, 8. 5, 6, 7, 8 will be maintained here, and here it comes as the 9th bit. Why? So this is the 9th bit, so the 9th bit comes here. So 9th bit is coming here, right? So these are the 4 bits coming as it is, these 4 bits. These 4 bits and these 4 bits and these 4 bits are represented here. These are the 4 bits chunks directly coming here, and the first and 6th bit, the bit 1 and bit 6 are represented here. These are bit 1s and these are bit 6, and both bit 1 comes from the 4th bit of the previous block, and bit 6 comes from the first bit of the next block. So this is the first bit of the next block, 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 like that. Okay, and this one, the 4th bit of the previous block, 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 and so on, right? So this is how the expansion P box works. Now the second component of DES function is the exclusive OR function, and this exclusive OR operation takes the 48 bits output that comes from the expansion P box, and the 48 bits key will be taken here and it will be performing the exclusive OR operation. So after the expansion permutation, DES uses exclusive OR operation, and this exclusive OR operation is performed on the expanded right section. What do you mean by expanded right section? Ri-1 is the right section which is expanded into 48 bits. So we call it as expanded right section, and the round key, which is the round key, Ki is the round key. Now here both the right section and the key are 48 bits in length, and also the round key, the Ki value is only used in this exclusive OR operation, right? So the rest of the boxes or the components are used only as confusion and diffusion boxes. So that is the second component of the DES function. And the third component of the DES function is the 8 S boxes, group of S boxes. So here we have 8 S boxes, and these 8 S boxes will receive the 48 bits and it will be producing the 32 bits output, right? So this is where the confusion is introduced. So lots of shuffling is being done. Okay, so what happens here? The DES uses 8 different S boxes, and each S box will have 6-bit input and a 4-bit output. Each S box. So 8 S boxes are there. You can see 1, 2, 3, 4, 5, 6, 7, 8. 8 S boxes are there, and each S box will take a 6-bit input and a 4-bit output. And the 48 bits data from the Whitener, which is the exclusive OR operation from the Whitener, is divided into 8-bit chunks here. So each 8-bit chunk will be transferred into a 8 4-bit chunks. Okay. So here the S box is again a table of a predetermined rule. Each S box has its own table of a predetermined rule. So this is how it is designed. 8 different S boxes. The 48-bit inputs will be divided into 6-bit chunks, and each 6-bit chunk is given into the S box, which will be producing 4-bit chunks. So this is the array of S boxes we have. So 48-bit input becomes a 32-bit output. Now internally the S box is designed like this. So if you observe here, 6 bits are given as the input and 4 bits are coming out as the output. Now for which the S box uses a table. So this kind of table will be used by the S box. So this is the table entry, different table. The table will have 4 rows and 16 columns. 4 rows and 16 columns. So 0 to 15 columns and 0 to 3 rows are there. So that is what is shown here, that is what is shown here. So let us see how these 6 bits input is producing the output. Now what it is going to do, observe here, in the 6 bits, the first bit and the 6th bit will be taken as the row index of the S box table, whereas bit 2, 3, 4, 5 will be taken as the column index of the S-box table. I repeat, bit 1 and bit 6 will be taken as the row index of the S-box table, and bit 2, 3, 4, 5 will be taken as the column index of the S-box table. Okay, so this is the table for S-box 1. The same way for S-box 2, S-box 3, 4, 5, 6, 7, 8, we have different tables. You can refer these textbooks for the rest of the S-boxes. Here I am showing only one S-box which is used as the S-box 1 table. So this is the predetermined rule we have. Okay. Now let us see how an input of 6-bit chunk given like this produces a 4-bit chunk of output like this. Okay. Suppose say imagine this is the S-box 1, right? So to this S-box 1, let us assume these are the bits given as the input. Where it is given? It is given here for S-box 1. So if S-box 1 is expanded like this with the table entry, so these 6 bits will be 1, 0, 0, 0, 1, 1. These are the 6 bits given as the input. So as indicated, the first bit and the 6th bit will be used for the row index, correct? So we write the first and the 6th bits together, which will be 1, 1 in binary, which is 3 in decimal. So 3 will be used as the row index. 3 will be used as the row index. Okay. Now the remaining bits 2, 3, 4, 5 will be 0, 0, 1, 1, which is going to be used as the column index. So this in binary will be equivalent to 1 in decimal. So we will have this as the column index. So row index is 3 and column index is 1. So we look for the value in row 3 and column 1. So row 3 and column 1 gives you value 12 in decimal. So which in binary is equivalent to 1100. So if this value is given as the input for S-box 1, using this method, it produces 12 as the output, where 12 is equivalent to 1100. So that is why we say the S-boxes are used to do the real mixing, and here the 6-bit chunk will produce a 4-bit chunk. So therefore, if 8 6-bit chunks are converted into 8 4-bit chunks, we will get the 32 bits as the output. So the input here is 48 bits and the output will be 32 bits. So this is how the S boxes helps in doing the confusion. And the last component of the DES function is the straight permutation. This one, not this one, this one. Sorry, the direction goes here, it is not here, it is actually the straight P box, it should come here. Please make a note of it. The straight P box is pointing here, it is not to be pointed here, it is actually pointing here, right? So the straight P box is expanded here. And the input for the straight P box is 32 bits and the output is again 32 bits, right? So it is simply doing shuffling again. the permutation for which it is using a straight permutation table, and based on this straight permutation table, the 32 bits input will be producing the 32 bit output, right? So this is the last operation in the DES function. Here the input output relationship for this operation is explained or shown in this particular table, and here, for example, the 7th bit of the input becomes the 2nd bit of the output. Here you can see the 7th bit becomes the 2nd bit of the output. The 12th bit of the input becomes the 6th bit of the output. 6th bit of the output. The same way, the 2nd bit of the input becomes the, here it is 1, 2, 3, 4, 5, 6, 7, 8, right? So 16, so 17th bit. So 2nd bit of the input becomes the 17th bit in the output. So this is how the straight permutation will be shuffling the bits for more security, right? So this is the DES function we have in the DES structure. We have seen DES structure, and inside the DES structure we have seen the DES structure diagrammatic representation is this, and we have seen these are the initial and final permutation done, and then we have seen the DES has 16 rounds. So each round in the DES will have these components, mixer and swapper, and the mixer is using a DES function, and the DES function has again 4 different components, and these components are explained here. The S box is doing the confusion and the P boxes are doing the diffusion. So this confusion and diffusion will do lots of shuffling, bit shuffling, so as to secure your data. So that's it about the DES function. We'll be discussing the key generation component which is used in the DES structure, the key generator, the round key generator we will be discussing in the next video. Thank you.